bit about work we're doing at Copenhagen at DICO, the Department of Computer Science in Copenhagen. During the talk, feel free to interrupt me at any time if you need to ask questions. So that way it's more interactive. I know Thomas's scope, right, of interactivity. Good. So the motivation for this work is coming from there has been kind of a sea change in how applications are being built, and we're seeing a lot more mobile applications coming up. We're seeing applications that are like across different domains, doing like a new kind of transaction processing in a sense, right? We had these old online transaction processing applications, and now there seems to be a new crop of them, in which you have systems going from all sorts of aspects of society, like for example, financial systems. Now you have like mobile payment applications. You have, for example, social network applications coming up. You have a set of different like computer games now are also played like in different, through different kinds of devices. You even have like a new kind of economic system, like the sharing economy, right? That is being created through these mobile applications. So a lot of new and different types of applications are coming up, and they're putting some pressure in the way we process and manage data for these applications. So what are some of these kind of characteristics of these new transaction processing applications? So we see some trends that, the complexity of application logic is increasing. So in the past, when people started doing transaction processing, the kind of benchmark we thought about was debit and credit, right? That was the thing. And now we do all sorts of complicated computations as part of a transactional application. Sometimes we're doing like very sophisticated modeling and simulations and machine learning and whatever, right? As part of these new applications. Except in blockchain, then we're doing only debit and credit again, right? So another characteristic is like latency, right? So latency is quite critical when you're using like mobile devices, for example, right? You don't want to be waiting for your phone, right? Like who does, right? So actually you want the interactions in those applications to be quite responsive. So things have to respond quickly. Another aspect of these applications is that scalability really matters. So we're not building applications like you can think of in the old days. We're building applications for a few people who would be like, I don't know, when I was growing up, like, my parents used like travel agents, right, for example, right? And then you had some people who are actually using the system, and there were a quite small subset of people. And nowadays we're building applications that we want everybody to use, right? Literally everybody. So the scalability level of these applications is much, much, much more intense, right? They're putting a bigger demand. So these trends are creating some, some natural pressures on OLTP systems, or transaction processing systems. And if we look at how, a transaction processing system is, a typical web application or a mobile application is architected, I mean, you would have like the classic solution to that was the 3-tier architecture. You had some kind of clients. These clients talk to an application server, and then this application server talks to another big server. So things are all nice and good. So the client makes a request. The application server has a bunch of logic. It will compute, think a lot about stuff, right? Okay. And to do that computation, it needs to access some data that isn't in the database. So it will send a bunch of database requests, and these requests will return to the application server, which will compute again, and then send the response back to the clients. So in that kind of architecture, you can almost think like that. This is the processor, and this is the memory. So that's sort of a rough way to think about it, right? Which basically you have like a lot of accesses going to this database system, and this is quite chatty. There is a lot of communication going on between the application server and the database. So if you have like latency constraints, if you need really quick response times, if you really need to compute a lot on data, right? Having this chattiness is not so great, right? But of course, like, the wisdom of ages has been that, well, you don't have to chat all the time with the database. You can, if latency becomes a problem in that kind of, in that site, then you can basically go and say, well, reduce a lot of the logic that was in the application server and move that into the database. Right? You move that into the database through different mechanisms. So for example, you can make your queries more complicated if you're like a really SQL aficionado, right? Or you can write things like stored procedures on the database. that sort of has been the wisdom, right, so far. Okay, so basically, like, you know, what people have been seeing is that, well, okay, these databases are kind of becoming, are having bigger demands. And to respond to those demands, there is a lot of research now on how to execute these programs, say the SQL or the stored procedures and so on, in the database in a way that is very, very fast, right? Both in terms of latency and also like very, very scalable. And the way to do that is to take advantage of advances in hardware. So nowadays, you know, we're moving to systems that are multi-core systems. So they have like a lot of parallel processing capability. They have large main memories, right? And even some of the disks are becoming solid state, right? Okay, so everything is kind of memory in a sense. And we have new database kind of architectures that are being designed to harness the performance of this new hardware. So basically kind of take advantage of this. On the other hand, the programming interfaces of databases have remained more or less unchanged, right? So we have SQL, we have stored procedures, and that's it, right? And if you're not happy with stored procedures, well, too bad. That's what we're gonna offer you, okay? So the question that we're asking a little bit in this work is, you know, with all these advancements and with all this pressure on data management technology, is this programming interface of stored procedures still good enough, right? Or are there ways in which we could try to improve that? So let's try to analyze when are these stored procedures, let's say, not good enough, right? So there are some challenges that come from using, you know, having code in the database. So one of these challenges is that, well, you have a set of challenges coming from software engineering, right? So stored procedures follow like a very old programming model, right? You have shared data, that's relations, and then you have programs, functions that access this shared data, and they can read and write to anything they want. So modularity is kind of an issue, right? You don't have a good mechanism to really like encapsulate data or reduce data dependencies or say, okay, my team works on this part of the system and your team works on that part of the system. So it's kind of hard to modularize the system using stored procedures. Another aspect that is challenging with stored procedures is that, you know, they lack abstractions to reason about performance. Like if you think about a typical stored procedure in a database, it's a sequential program. You essentially write your program as if you were the only one executing in the world. Actually, that's why transactions, right, are there, so that you have the illusion that you're the only one executing in the world and that everything is sequential and nice, right? So it's very hard for you as an application developer to say, well, I want to change my program now to use parallelism, right? What if I know something, right, okay, about things that are independent that could be processed in parallel, right? There's no way for you to necessarily express that to the database directly. On the other hand, there are some performance challenges, right? So for example, you know, if you take kind of the traditional approach for improving performance of database queries, for example, is to use data partitioning, right? And in many cases, that works really well. When you have a lot of data, that works great, right? Because you're partitioning the computation across different data elements. But what if you have a mix, right? I mean, a mix of computation and data, right? If you have like heavy functions being applied on data, it's not always the case that you can, you know, make data partitioning work. There are other performance challenges. So for example, with stored procedures, it's quite hard to kind of manage locality because of this modularity issue, right? So you can access any kind of relation. You have no low-level control over how your code is deployed. You can actually control how the data is deployed in the database. So you can say, I'm going to use data partitioning, and therefore I can allocate certain fragments to certain, you know, compute nodes and stuff like that. It's much harder to allocate the code that is running, right, to certain compute nodes or fragments. Essentially, databases typically give you no control over that. So these are lots of challenges, right, to the programming model of stored procedures, right? And then you think, well, is there a way that we could try to address all of these challenges, hopefully in a holistic way, right? And we wagered that there is a model that's been out there for a very long time. It's a very old model of computation that actually has some features that we should examine. They're interesting features for data management applications. Okay, so for example, this is called the actor programming model, right? It's implemented in a number of frameworks. I think you have I know some people in the room have used some of these, right? Okay, at least from talking to you. So for example, ACA is one model, one implementation of the actor model in the Java ecosystem, or JVM ecosystem to be more generic. You have Erlang, you have Orleans from C# ecosystem. So you have like a bunch of implementations out there of the actor model that are coming up. And they promise you these kind of very nice characteristics like modularity, asynchrony, concurrency, so that you can actually express all this stuff that is lacking in your kind of classic stored procedure programming. So what is an actor anyways? Okay, so the way to think about an actor is, you know, remember we had separated like the compute from the memory, right? An actor is just kind of putting these two together and, you know, having like modules that unify computing and memory. So you can think of an actor as a little module. It's a logical module, right? It doesn't necessarily correspond to a processor or to a node or anything like that. It's just a logical abstraction that has like, it's distributed, so it's separate from other actors. It is single-threaded, so for example, you can think of it like it has a single thread of control, and it has some internal state. It has some private state. And the state of that actor can only be accessed by that thread of control, the one of the actor. And if you want to, you know, access the state of another actor, you have to send a message to that guy and say, hey, can you please do a computation for me or return me some, you know, data, right? So this is basically the idea. And you then architect your application as a distributed application. So the way to think about actor programming is, well, in the past, say with stored procedure programming, you architected your programs as single-thread sequential programs, right? As if you had a massive single processor that could process everything, right? So you're hiding distribution. And in an actor programming model, you're actually exposing distribution, embracing distribution. So you already architect your application as a distributed application and then find a way to execute it on current hardware. So this seems to be interesting, right, as an idea. So the question that we're asking is there then a way to bring together these two kind of worlds, the world of actor runtimes and of relational databases? So we have all sorts of stuff that we like about relational databases, right? We have physical data independence, we have like, you know, transactions, so high consistency of data management, we have recoverability, we have like all sorts of cool features that the database provides to us, but we have these programming challenges with, you know, modern applications. So we're going to try to explore an idea of an actor relational database. So how would that look like, right? A database that actually brings together these two worlds. And in particular, the question we're going to be thinking about is how can we integrate an actor programming model with a modern relational database system with high performance. Okay, so you could think of different questions, okay, to explore as well. For example, how do you integrate database features in an actor runtime would be a different question, right? But today we're going to explore the other direction. If I have like, you know, database systems, how do I bring this actor programming model features to, say, stored procedures in databases? Good, so the roadmap for that is we're gonna start from a relational actor programming model. So we're gonna try to think about how to change the programming model to include the actor model in the database. And then we'll look at a prototype relational actor database system. So the programming model we call Reactors for relational actors, and the system is ReactDB because it's a relational actor database. Okay? And then I'll show you a little bit of an evaluation and conclude. So let's start with Reactors, okay? So just to have a running example to show, we need to show some application code to see how this programming model could look like. So let's think of an application of, you know, very simplified digital currency exchange application, which is kind of all the rage nowadays, right? Okay, it's kind of debit credit all over again. So where you have like, you know, some wallets, right? In which, and different providers where you can settle, you know, digital currency for fiat currency, for example, right? And then you have like, these providers are kind of processing orders for settlements, and then you have an exchange that is actually having the hard job of doing the, the swap, right? So you can think of it like that, whenever you have clearing, like settlement, what's going on is the exchange is holding the risk for a certain amount of time, right? You say here, I'm gonna give you some dollars if you give me some digital currency or vice versa, right? But until you actually clear, right? Until you actually transform these dollars into digital currency, the exchange is kind of holding the, holding the order kind of and, holding the risk, right? So you can think of like modeling this with a relational database, as usual, right? It's kind of the thing that we do. So, well, okay, so the exchange could have one relation that says what is the settlement risk I'm willing to tolerate, like how much exposure I can have in open transactions out there right now, how much risk I could want to have globally or per provider, right? And I could have a provider relations kind of capturing all these providers that, say like how much risk I'm willing to tolerate, say, right? It says like, also, the last time I computed this risk based on some model. I don't know, one Markov chain kind of thing, I don't know, like a Monte Carlo Markov chain, whatever, computation to update that. And then I have a bunch of orders that my customers put on their wallet saying, okay, I want to settle some value of currency and then, make this exchange. And at some point this will settle. So some of them are settled, some of them are not settled. Good, so what is a reactor now? We'll use that application as a running example, okay? So a reactor is gonna be an application-defined actor. It encapsulates the states as relations. So you can think you have a thread of control, and you have some relational state. So since it is an actor, it's single-threaded, and it's concurrent, so it's all distributed, right, logically speaking, and isolated, but the state is relational. A reactor type has some schema and some methods associated to that. And a reactor instance has a type and also a unique name assigned by the programmer. So you can address that reactor. And you can think of them as like they are in existence forever. Okay? It's as if I had a namespace of actors, so I don't have to create and destroy them. They're always there. Okay? That makes things more convenient. So for example, as examples of reactor types, right? So I could have a type definition for the exchange that has some relations like the settlement risk, maybe the provider names that I know of this exchange, a reactor for type for providers that has the orders and the information about this provider. And you could have some methods, I don't know, authorize a payment on the exchange, right? Which might trigger some methods like, I don't know, calculate the risk on the providers, or add an entry to an order relation in the providers, right? So that could be like a way to model this. So as we're modeling the reactor types, you're already kind of creating a distribution, right? You're already saying like, my schema, somehow parts of it are in the exchange type, parts of it are in the provider type. So it's no longer a global schema, right? You already kind of started distributing it. And you have reactor instances. For example, I could have one instance for the exchange, let's say, a name could be one exchange, right? I don't know. And then you could have one reactor instance with different names for each provider that is out there. One for MasterCard, another for Visa, and so on. Okay. So within a reactor, you can use declarative queries to access the relational state. So that means that if you have like any kind of relational schema incorporated inside a reactor, by modeling of the application, you can basically kind of go from very different extremes, right? You could think of like a traditional relational database is actually like a reactor database with a single actor, in which all the relations, all the schema is inside this one actor, right? But now you can start decomposing things, right? You can go to the other extreme, like a key value database. I don't know, people might like things like MongoDB or whatever, right? Okay. So that's like a Reactor database in which I took all the tuples and I put like each tuple inside a separate reactor, right? So that's like the maximum extreme of distribution. And you could have any kind of thing in between, a hybrid kind of decomposition. Could put some fragments of relations inside certain actors, like decomposing them vertically, horizontally, in any kind of way you find reasonable. Okay. So that gives you a mechanism for modularity. Okay. So, and you can actually write, like for example, if you have some a method like calculate risk for a given reactor, you could write like declarative queries in SQL, just the usual thing, right? The only constraint is that you're accessing the relations that are encapsulated in that reactor. Okay. Now, how do you access relations that are in another reactor, right? because now you distributed the state, right? So how does that work? So now, well, in the actor model, you do that by using asynchronous function calls. So you basically specify a reactor name, send a method invocation so that that other reactor can compute on that, and you get like a future result. So the interface for that is something like this. I invoke a function on some reactor, and then I'll get a future result. That means this result will become available at some point in the future. And I can synchronize on that future, like say, get me the result now. And if it's not there, I'll just block, okay, until it becomes available. So that means that, you know, now as you ship things out to other reactors, you can basically think, well, all this processes overlap. So this is happening concurrently in other reactors in the system. So at least from the point of view of the programming model, this gives you a way to structure application to leverage parallelism, right, at the application level. It gives you an abstraction to reason about performance, and the reactor encapsulation gives you some abstraction for modularity as well. Okay, so we're going in some way in which stored procedures are getting a little bit more interesting, right? Let's put it like that with reactors. So just to give you an example, so if I want to authorize a payment in the exchange, so I could, for example, look at all the providers, like, I don't know, I could take a look at the settlement risk that I'm willing to tolerate. And for the providers that are out there, I could ask to calculate some risk on these different providers, right? And then collect the futures, eventually synchronize on these futures, and then see, you know, if my risk is below my tolerated risk, and then actually accept the order or reject the order. Okay, so that would be one way to think about that. And when you calculate risk on different providers, you can think that this is happening in parallel, right? Or at least it's, from the point of view of the programming model, it's concurrent. Whether you process it in parallel or not is another question, right? But it's definitely, these are independent tasks that you shipped out to be executed. Good, so there are some semantic issues with synchronization, because what happens is, well, if you go back to such a program, I mean, you wouldn't like to be thinking very deep and hard about, you know, well, now I sent this message to another provider reactor. What if something else interleaves? Okay, now the exchange is kind of blocked, and you know what happens to the other providers and the other messages that are scheduled and so on, right? So in databases, we know that, you know, transactions allow you to forget about all that, right? You just have a consistent result in a multi-actor interaction. That would be the ideal world, right? So we want to kind of maintain transactions even across multiple actors, right, in a relational actor database. So that creates some semantic issues for us to think about. So for example, when you invoke some method in the same reactor, what is the semantics of that, right, okay? So if you have modularity, right, it would be very odd if you couldn't call a method as part of another method, right? I mean, that would be very disturbing, let's put it like that, okay? So, so basically, you can do that with stored procedures, right? You can call a procedure from another one, and you should be able to do that, right? So since reactors have, like, they have a single logical thread of control, you can think of these methods as automatically synchronous, right? So if you call a method on yourself, you immediately get the results. It's kind of executed directly. So it's not like a parallel execution, right? And if you want to execute methods on other reactors, then since you have transactions, the parent methods only completes when all the children methods are finished. Okay, so basically, like, for example, here, the method that A triggered on B, C, the method calls, right, and D, then the original client invocation will only finish when all of these guys are finished, right? And that can be recursive, right? So I could call on E and F and so on and so forth. So when these conclude, then these guys can conclude, and you know, and then when these guys conclude, then they can conclude, right? So another issue with providing transactional guarantees is that, you know, you wanna provide for serializability, right, and all the other transaction properties. That means that, you know, unsafe program executions need to be controlled, right, somehow, right? So in the same way that, you know, databases use concurrency control and give it this nice transaction abstraction, somehow we should be able to have similar mechanisms in a Reactor database. But here the problem is a little bit more complicated, right? Because now you distributed the state. So that means that you can have things like this, like, I could have a method from A that calls a method on B, and B calls an asynchronous method on A. So that creates like, a circular dependency, right? And if an actor is single-threaded, you never, and you're blocked here, you never dequeue, to process a method call from the other guy, and then you're kind of in trouble, right? So we call this kind of dependency unsafe program structure, right? And we'll detect these unsafe program structures and abort the transaction when they happen. Okay, so these are programming restrictions, you can think of it like that in the Reactor model. And another way to have unsafe structures is also to say, okay, you could be calling from different paths on the same actor, right? And that means that now you would have a race within yourself, right, within the same transaction, right? So that would also be a kind of unsafe structure.
So what kind of concurrency semantics? I mean, the databases, you have all this two-phase locking, rigorous. You have timestamp-based concurrency control.
Yeah.
What is the main idea behind the concurrency model here? Is this like all manual? Is this like with waits for graphs, identifying cycles and abort them, or?
So the way that we're doing is, okay, so there are these restrictions of unsafe programs. So whenever an unsafe program is detected, we'll abort them, right? Now, if you look at the set of safe programs, right, then we have a proof in the paper that this is actually syntactic sugar over traditional databases. You can actually reduce everything to conflict serializability as you define in traditional databases. So for all safe programs, you can actually reuse all the machinery, right? So if you liked all that stuff, timestamp concurrency control, OCC, like two-phase locking, 2PC, everything, you can reuse everything. Like, okay, so it's all available for you to use to implement Reactor, a Reactor database system, right? Something that will actually
Reactors.
Yes, exactly. Actually execute Reactor programs. So the only constraint is disallowing these unsafe programs. Right, and that we have one condition in the paper, which is whenever you have two execution contexts active at the same time on the same actor, then we abort, which is like a simple check, right? But you could come up with other ways to avoid, unsafe programs as well. Good. So well, you already yes, anticipated, right? The natural question, right, which is that we want to reuse all that machinery, right, of database systems. So once you are in the safe subset, you can formalize an equivalence, and then you're safe to go, right, to use all of the machinery you had before. Okay, super. So questions so far about other questions, right? So far about the Reactor programming model. Yes.
I have a question about the queries between the reactors.
Yes.
What about the join, let's say, because
Yes.
you show a simple query that joins to Reactor.
Yes.
How about the more complex, let's say, join, where a relation is in one reactor and
Right.
another
Right. So that's like definitely something that becomes harder to do in Reactors, right? Because now you would have, since you don't want to break encapsulation, right? So because of that, you would have to kind of pipe things with this low-level concurrency assembly, right? Which is essentially kind of sending, procedure calls, asynchronous procedure calls, and dealing with the futures and all that, right? So actually executing a join becomes a lot more complicated because you're, now actually piping the data around yourself in the application, right? It would be super nice to have some higher level abstraction than concurrency assembly, but at the same time maintain the property of encapsulation and maintain the idea that this is a distributed computation, right? For example, you could have some way to create an actor workflow, for example, right? Yeah. So, but we haven't done that yet.
Okay, so the idea is to ship the data to one reactor and to the join there.
Or, you could ship the data to, you could ship between them, you could ship to a
Yeah.
third one, you could do a lot of things, like, yes, you could do a lot of different possible implementations, right? You could even have, so I think that it would be interesting to have models of multi-actor coordination or interaction, right? Right now, in the base definition of the model, we started with just asynchronous procedure calls, that means that the programmer has to do that plumbing, right? Which is tedious, right? But it would be nice if we could not have to do that plumbing, right, in the future. Yes?
I would like to ask you if you evaluate the reactor model in distributed environment, not in a single machine. So do you have any delays there? Maybe some barriers because if you want to wait from all the nodes of the distributed system to collect the data, so you have performance issues here. So
Okay, so we're getting into the performance issues, right?
Yeah.
So that's good, because that brings me to our next, point. How do we implement this stuff, right? Okay, and I'll try to argue here. We have an implementation of the Reactor model, right, in an in-memory database system. So that's a single node implementation. I'll show you in a second that the way we architected this is actually trying to think of a single node as a distributed system. So that way it will generalize quite well, I hope, right? Okay, to more distributed setups. So let me go quickly through that, and then we can actually have a discussion about your point, right? So in-memory database architectures, they usually have this problem to solve, which is you have a multi-core machine with a very large main memory. They have lots of processors, right, potentially. And now we have to map these reactors to, all this processing infrastructure that is out there, okay? So how do we do that mapping? So you could start by saying, well, let's use some operating system abstractions and just use that and, say, for example, map reactors to processes or threads, right? Man, but that's kind of lots of overheads, right, if you do such kind of mapping. And you also lose, at the database level, a lot of scheduling flexibility and control over how to schedule these actors at a fine grain, right? So that's what you would like to retain and not give up that to the operating system, right? So the way we kind of architect ReactDB is essentially we have a couple of building blocks. One we call transaction executors. That's abstracting a physical core, and you have containers that abstract a set of physical cores, right, and the memory shared between cores. And now we can start thinking of the problem in a different way. You can map transaction executors to containers. So you can think each container is like a node, right, quote unquote, even though it's like a virtual node, right, in the case of a multi-core machine. And you can map reactors to transaction executors such that a reactor belongs to a single container. Okay, so you cannot have a distributed, reactor itself, right? Okay, so and you can do that mapping at deployment time. So that can be, it's now specified directly as a configuration to our system, but hopefully in the long and glorious future, we'd like to do like automatic optimization of these deployments. So the way to think about it is, well, in a multi-core machine, you have a bunch of containers. Each container has a lot of components, like transaction executors pinned to these cores. They have different request queues or transaction coordinators, coordinate transactions with other containers, right, in the system. Transport driver kind of makes the, data shipping between containers. So you see, it's very similar to a distributed system type of architecture. And you have like transaction routers to decide where to put a transaction call within one of these transaction executors. So now you can start thinking of how to model different database architectures. So a shared nothing architecture will look something like you have a transaction executor and you map reactors to particular transaction executors, but not too many, right? So for example here, reactor A is only mapped to this one transaction executor, right? And reactor C and D, for example, only to this other one, right? And you have two different containers, so these are really isolated, pieces of memory. So that's a shared nothing style approach. What if you want to do like shared everything architecture, right, for a database system? Like use shared memory, actually, execute the code and execute like memory reads, right? Then you could, for example, deploy reactors to all transaction executors, and then load balance the transaction calls to these reactors across transaction executors. That's another way to do a deployment. You could also like do things that are a little bit different. So, a lot of recent results in memory transaction processing show that, affinity matters a lot in modern processors. So for example, if you're accessing always the same data on the same core, you get a big performance boost by doing that, right? So So you could like model such kinds of decisions by saying, well, okay, I'm gonna deploy reactors A and B only on this transaction executor, and C and D only on that one, but now I can access any memory within the container, right? So, so the way to think about it is, so that would be like without affinity or with affinity to data, right? To processing elements in data. So the way to think about it is, by these kind of different deployments, you're finding a way to like, when you do a future call in the programming model, you can actually execute that in a separate element, right? Like that would be in the case of a shared nothing, right? So here you would have really, you would ship the code, right? Or ship the call, right? From here to there, right? To execute a call on Reactor from B to C, for example, right? And in a shared everything setup, what we would do, we would completely sequentialize. Like if I'm calling from B to C, I will not ship the code there, I'll just kind of execute directly on this core and access all the data of C via shared memory, right? So I'm breaking encapsulation only inside the system, but in the programming model, it's all nice and clear, okay? So these are different ways in which you can basically like now either sequentialize the processing, right, of a particular, function, or you can actually, expose the processing as parallel processing, right, in physical parallel processing, right? And the intuition of that is simple, like if you model your application as reactors, you could have, I don't know, many more, like hundreds, thousands of reactors, right? While, you might have only a few tens or hundreds of processing cores. So it can actually, sometimes you will need to sequentialize, right? Not everything will be parallel. Okay. Good. So there are lots of details. I'm gonna try to not say much about, right, in the interest of time, on how you implement such a database system, or the transaction processing element of such a database system, related to how you manage threads and which contexts are alive at any given point in time, and how you minimize context switches, and how do you do the concurrency control, which protocols to reuse, right? Should we use, like, for example, nowadays state of the art is typically using optimistic concurrency control protocols, right? How do you leverage, like, how do you do like multi-container coordination, like how do you actually pipe the execution between different containers, and how do you represent the data, and which kind of data structure you put that, and so on and so forth. Okay, so there are lots and lots of details. In our prototype of ReactDB, we have implemented, taken a number of these design choices, right? Trying to leverage as much as possible state-of-the-art in-memory database technology. One thing we didn't implement yet on the transactional component is durability. Actually, we're implementing it right now. Okay, so this is coming. So I'll show you some numbers now of ReactDB and reactors, but these numbers are in-memory numbers. Okay, so they're not with persistency. So what kinds of questions we asked about ReactDB and reactors? So we basically looked at, can we really leverage these gains, right, of a synchrony, right, somehow, right? So what we have observed is, like, let's say we have an application, just to use the same kind of application we had before, the digital currency exchange, and I have some authorization of payment program, and I could, like, now use a shared everything deployment to sequentialize, so everything is like sequential logic, right? I could use like a Reactor program formulation in which I only parallelize queries, as if I were parallelizing queries in SQL, for example. Or I could now parallelize queries and risk calculation, which is part of the procedure code, right? So now I can parallelize stuff that includes, like, updates and complex code and all sorts of stuff together, right? So if you try to do that, you see that there is like a trade-off, like how much parallelization is helpful depends on how much logic you really have available to parallelize, right? If you have debit credit, well, you can execute debit credit over multiple cores, but maybe you're not going to get a lot out of that, like, okay? But if you have a complex simulation or a complex machine learning model, you might gain a lot by executing things over multiple cores, right? So we try to vary that by basically varying the complexity of a risk simulation function by generating random numbers, more and more of them, and see where the curves kind of cross each other, right? Okay. So So here's what we got. So you can see that procedure level parallelism actually starts giving some gains at some level of computation, right? With respect to even query level parallelism or sequential, of course. Right? And these gains, if you have a lot of compute, you can get very large gains, right, by using parallel resources for the procedure. If you do not have a lot of compute, then we are getting closer and closer to being similar to like query level parallelism, right? So, so whether you gain something really depends on whether you have more computation in the procedures to parallelize, right, with the reactor model. And these gains, they vary a little bit. So for example, what if I were like executing on a database that is quite loaded, right, that has a lot of clients executing at the same time? That would mean that the amount of resources, the slack that I have to use for parallelism is not very high, right? There's not a lot left, right, for parallel execution of reactor calls. So basically here we instrumented to BCC, right, with a little bit of extra computation, right? And we compared different deployments that show you the effect of leveraging parallelism or not in a reactor system. And you can see that, there is like a trade-off here in which, when you have low load, like, not many clients attacking the system, you do get like, some benefit from asynchrony because you can use the slack of parallel resources. And when you have high load, then you're getting better, then it's better to just sequentialize, right? Okay, so I'll skip the last experiment. We can talk about it later, which is just about like latency. And there's a lot more also in the paper that we have described in reactors. But to finalize, to conclude, what we talked about today is a new model for, given this trends in new OLTP applications and modern databases, we have complex logic, we have latency, and we have scalability challenges. And we're looking at, these trends call for rethinking like stored procedure programming models in databases, right? And we're proposing a Reactor programming model to marry Reactor programming model with relational data model, and a system that shows you how to leverage this programming model to control, for example, database architecture, and either express or sequentialize programs in the Reactor model. So, thank you for that.
So, is there any question from the audience? Yes.
I will try and make it a very short question. Try and transfer this to again to innovation design we talked earlier. Now, in non-linear environments, it's important in innovation design, instead of focusing on risk assessment, to structure the innovation, the new innovation, in a way that there is more upside than downside from variability, randomness, and time. Mm-hmm. Now, how would this model help us to build in the innovation this capability of automatically having more upside than downside, rather than focusing on risk assessment? Mm-hmm. So that it's a concept of anti-fragile from Nassim Taleb's approach.
Right. So I think that I used the risk simulation here in the examples, right? But I'd like to say that the Reactor programming model is a general programming model, so it can actually encode any procedure logic that you would like. So if instead of risk you would like to use another kind of model for assessment, that would be perfectly reasonable and supported by the model as well, right? So so it could also encode other methodologies different than risk assessment in the procedural programs. And that's actually one of the nice aspects of the model, because you get to write like very complicated programs, right? And you don't have to necessarily squeeze everything into SQL, right? As a logic, but you can actually write programs that are, encode different kind of beliefs, right? Or belief systems about, the application domain.
Okay.
Any other question?
So, yeah. So my question is that, so
for the implementation techniques that you have presented, so which part is actually particular to like Reactor model, right? Comparing to just actor models. Right? A lot of things you talk about like related to just actor open frameworks.
Right. So you have this flexibility in deployment is actually quite interesting because you're actually doing concurrency control, right? Which is something that typical actor systems do it in a different way you can think, right? Or they don't do it in the database way, right? So like the typical actor system, I mean, you wouldn't be able to say like one actor is executed by a thread at a given point in time, right? But you can't have one actor being executed by multiple threads at the same point in time. So that's something that is possible in ReactDB, right? You can actually do that because you can use concurrency control, and if there are no conflicts, it's like conflict serializability tells us that we can create a serializable schedule and all that. So this is something that actor platforms typically don't do, and that we can do actually, for example, for using aligning database and actor technology.
Okay, thank you very much. Time is pressing, but we will have follow-up time, and because the question came from the next speaker, so we can maybe pipeline. But so let us thank the